Hello. My name is Chang Pyo, and English is not my native tongue, so you may have some difficulties in understanding what I'm speaking. So you may stop me anytime if you cannot understand what I'm talking about. And I'm a professor in the Seoul Phonix University, teaching programming languages and compilers. And we're here together with my students, Hyundu, is assisting me. And today's topic is about how we can protect binary executable programs made from the C and C++. If you don't mind, then let me sit and speak it. I have to see that script. Memory is always vulnerable. So most attacks against the program targets memory. So among the parts of the memory, attackers aim at the data area here. Defining further, attacks usually focus on compromising code pointers. So with the compromised code pointers, attackers can divert control flow to the locations they want. I think that Robert explained it much about it. Or they can disclose control information such as return addresses. So let me see. A typical memory attack is the well-known buffer overflow attack. I think we already acquainted with the concept. So overwrites beyond the boundary, so that a nearby code pointer is set to an address that attacker desires. So when the pointer is dereferenced, then the pointer points to some injected code. That's robots call that code injection, or sometimes that the compromised code pointer may lead to some already existing instructions. That's what's called the arc injections, or return-oriented program. The attacker's destination may be somewhere in the program already in program. So from the destination, the illegal control behavior begins. Finally, the attackers may get a root privilege or disclose critical information. So when you get a root privilege, opening a shell with root privilege, then he can do whatever he wants, destroying the system or getting all the information from the system. And this is some tutorial for the buffer overflow. Normal control flow returns to the caller when the return instruction executed, and the control flows from the core side here. But if the attack is compromise the return address here, then the control diverts to some malicious code as attacker intended. So that's a usual buffer overflow attack to compromise return addresses. So another aspect I'd like to emphasize is information leak. Sometimes attackers inject a bunch of bits into the victim program. Then depending on the victim's response, they can confirm if the injected bits are the same as those already in the victim's memory. If nothing happens, then the injected code is what they are. So they can collect byte by byte incrementally, and collecting that after collecting the enough byte, then they can analyze them and use the collected information to see what it is in there. And attack may start new attack using the collected information. So I noticed that Robert mentioned the ROP attack, but some ROP attacks starts without assuming anything, just leaking every bytes from the memory. Then they begin to expect what's there, even they do not know that what the operating systems or what's the processor is. But after they collecting a bunch of bits, then they compare it with the known bit patterns, and they can see that what the systems are, even the processors are. Then once they get it, then they design some new exploits using the disclosed information. I will demonstrate on that attack later. So the code pointer problems can be observed in many applications. And this year, though the code pointer attacks by buffer overflow have been wrong since they were born, they are still around us. WhatsApp was vulnerable to buffer overflow, and attackers can remotely install spyware in the target smartphone by simply calling the target phone. That's caused the buffer overflow and the code pointer attacks. Another incident is a PostgreSQL vulnerability. And this has also happened in this year. And PostgreSQL is open source DBMS, and it also has the vulnerability of a stack-based buffer overflow. And attackers can get PostgreSQL crash, or they can execute arbitrary code. Final example of a code point problem is Ghost vulnerability. It's 4 years ago. It was a vulnerability in the Linux glibc library, standard C library, and it has a buffer overflow vulnerability. And attackers can get the root privilege through this Ghost vulnerabilities. Then how we can mitigate the attacks on the code pointers? There are, if I would include what Robert mentioned in this, developing the code securely, then we can think of the three choices. But here I listed the two things, what can be done using some tools. One approach monitors and control flow, and the other is obfuscation of memory. So monitoring is looking at closely that what the programs moves around the program. They compare the control flow with the control flow graph, which is built previously before program is executed. Program can predict its code pointers by monitoring the control flow or obfuscation of its components and memory. So obfuscation can be done in randomizing the location of components, or we can randomize the content space inside it. So they can be done at the same time, but then the overhead will increase. So people choose one of them. Randomizing the location, that's called the famous one is ASLR, other space layout randomization, and the other is encryption approaches. And the criteria for the selection depends on the effectiveness of mitigation, and the other is criteria is cost. Well, I noticed that in the C programming community, even though that the mitigation strategy is really fine and good, if it takes really much time, then people are willing to adopt the protection scheme. So it's really important to make a balance between the effectiveness and the cost. And usually the monitoring-based approach is cost high if we reduce the grain size to a really small one. So to meet the cost requirement, they increase the grain size, then they may lose some attacks. So, I mean, they cannot detect some really fine attacks if they increase the monitoring grain size. So comparing the approach, the address space layout randomization shuffles the locations of the component. So it may take a time before the outside adversaries to find out where all the components are, because without knowing that the location of the components, they can start any attacks. Contrastingly, the encryption-based approach prepares a secret key and encrypts the code pointers. So encryption-based approaches insert code for the encryption at compile time. Usually they use an instrumentation tool to insert the code to encrypt return address and a function pointer, something like that. At runtime, the inserted code encrypts code pointers, and this is the approach we are taking. Zeus takes the encryption approach. Sorry about that. Let me see. There has been some new attack method. So one is the blind RP, which I mentioned a couple of minutes ago. It's a return-oriented programming without assuming that anything. They just try to disclose everything in the memory, and they begin to analyze the bits, and they begin to confirm what the system is and where all the text segments are, data segments are, before they construct any exploits. The blind RP is supported by the crash resistance oriented programming. Crash resistance programming is really easy with web servers. Web servers are configured to restart whenever they crash. So attackers can inject whatever they want, but the system may crash, but the web servers usually launch a new thread or process. So we can try to read out the memory space of the web servers whenever we want. I show it in a demonstration. And another technique is incremental byte reading. And incremental byte reading is a really simple idea. If we were to extract all the 4 bytes address in a 32-bit system, then in the worst case, then we may have to try that the 4 billion times to guess the 4 bytes word. But if we try that 1 byte at a time, then we may just try that 1,024 trials, because if we want to break a byte, then in the worst case, we may try that 256 times, right? 2 to the power 8 is 256, and byte after byte, and the 256 times 4, then it's 1,024 times, say enough to get all the bytes. So incremental byte reading and the crash resistance programming can assist at the blind RP greatly. So it facilitates the brute force attacks for the information leak. It's a kind of a prelude for the main attack, leaking everything, and then we can analyze the leaked bits and construct some exploits and inject it back again, then the attack succeeds. This kind of a blind ROP crop of incremental byte reading seriously diminishes the effectiveness of encryption-based approach. Encryption-based approach is not it's not a new idea, but it was welcome because its cost is really less expensive compared to the monitoring approach. Anyway, so our countermeasure against this kind of information leak attack is promoting all the memory system as moving target defense by re-encryption. That's the main idea of Zeus systems. So let me go briefly what the Zeus system does. Zeus defense against code pointer attack is it's basically encryption of code pointers. But to strengthen or to fortify against the information leak, it promotes that the return address is a moving target. It's, we dynamically re-encrypt return addresses from time to time before control flows moves into the vulnerable area. So Zeus can mitigate control flow interception as well as leakage of code pointers. And the current status of development, all the return addresses are dynamically re-encrypted. So we have done implementing it and it's submitted for the US patent. And other pointers, for the function pointers, we can classify them into the 3 groups or 4 groups. Among the function pointers, one is the PLT and GOT. These pointers are used to connect to the shared object and libraries. We have done the design for the dynamic encryption, re-encryption of the GOTs. And it's also submitted to the US patent too. And static encryption of this function pointer is already done and we got the patent. And another hard part is the programmer-defined function pointer and the compiler-generated function pointers. And anyway, we can protect these pointers by static encryption. Static encryption means no re-encryption at one time, just a one-time encryption. But the encryption state does not change throughout the program's lifetime, the execution time, but it's really hard. Let me explain a little bit more about the programmer-defined pointers and static encryption. Zeus's approach to static encryption of programmer-defined function pointers are notable. Encryption of these function pointers was tried a long time ago, what is called the point guard. It's quite a long time ago, but there has been no paper or news reporting the complete implementation. I guess point guard was stopped by the difficulty caused by the typecasting and pointer aliasing in function pointers. Because this typecasting and the pointer aliasing, it's really hard to trace which function pointers to keep track of for the re-encryptions. It's really hard. So if we re-encrypt those function pointers incorrectly, then a program would crash, even there is no attack. So to preserve the correctness, the alias analysis cannot be trusted for the re-encryption. I think that's why the point guard people kit in the middle. Zeus's approach circumvents the difficulty by encrypting function symbols, not the function pointer variables. While using our Zeus compiler, we can build standard C library and some server programs such as Apache and Nginx and programs. How Zeus compiled the program responds to attacks on the code pointers. Overwriting code pointers without using correct encryption keys would end with crash, because matching the decryption would make the overwritten address an illegal pointer values. Zeus can make the program detect attacks and invoke exception handlers. It's an adoption. Detection is an adoption by Zeus by dual encryption. We can encrypt the code pointers with different keys, and when we dereference the pointer, then we decrypt it again and compare these two. If there is an attack, then there is a difference between the two pointers, which should be the same. But in our opinion, the detection method is not good, because the attacked programs, the memory state is already contaminated. So it's not safe, or it's not wise to continue the computation with some risk. It's not a good idea. So I think just the crashing the attacked program is much better. And also, Zeus can make programs. Another advantage of the Zeus is there would be no leaks of return addresses on pointers to shared library function. These two are really important information for attackers, because they can design exploits or attack payload using those pointer information. So and also resilient programs are configured, as I mentioned, configured to automatically restart themselves whenever they crash. Zeus compiled resilient programs dynamically re-encrypts return addresses and some other code pointers. Thus, resilient programs may experience frequent crash, but they do not disclose any dynamically re-encrypted code pointers. Well, the Zeus compiled programs response, in short, they may be crashed, or they may continuously revive, but there will be no information leak. That's what the Zeus has accomplished. So let me show you some